and we're going to continue with the concepts we had before. If you recall, we finished the content of the chapter. We talked about work and energy. I'm going to make very brief review. We talked the work done by force. We calculate the work of some famous forces, let's say gravity, spring, and friction. Then we talked about work and energy. We literally integrated the work done by force on a curvilinear path and developed that the work is used to change the kinetic energy. Then we talked about conservative forces, that their work does not depend on the path of motion, just initial final point, like gravity, like spring forces. We use them to define potential energy. And then when we did the work energy relation, we separate non-conservative forces and conservative forces. This part goes into potential energy. And if you do that, you can simplify, I wouldn't say simplify, rewrite the work energy relation as the initial mechanical energy of the system and the final mechanical energy of the system are affected by the work of non-conservative forces. And if there's no non-conservative force, means initial and final energy is the same, which means the amount of mechanical energy of the particle will be constant if there is no non-conservative force, which means there's no friction, there's no pushing or pulling. All you have is the springs, gravity, and the particle moving. And if you have a system of particles, you can add all mechanical energy of the system before and after, so make it is constant. Now with that, let's go to this example. A roller coaster. I'm sure you all have experienced this fun activity, right? Oops. Roller coaster. Any one of you have never been to like amusement park like Disney or whatever else? You all have seen this, right? Well, I'm going to ruin your life. Next time you will be in amusement park, remember every ride you take has this mechanical energy, conservation of energy and stuff like that. They're built based on technically dynamics rules, right? So hopefully when you get the ride, you think of dynamics and enjoy the ride even more, or maybe you hate it, depends on. So you have this roller coaster, and you may realize that every roller coaster, no matter how big or small or complicated they are, the passengers come up like a ramp to the highest point. Technically, we give them some potential energy, so increase the energy of the particle, which is the cart or people in the cart altogether. And from there, that potential energy will be used to create kinetic energy going around up and down up to the end of the path. Because there's friction on the way, as you move forward, the overall energy of the system will go down because you have non-conservative forces that consume some of those energies. And I don't know if you guys have ever noticed, in certain areas, there's also brakes, right? Sometimes when you get to the top or you're going down, there's little brakes, so slow down so that you don't want to go all the way up to the highest level. So you want to go slowly down and, you know, minimize your speed, so at the end you can stop. When you have brakes technically is friction, right? And the work of the brake is negative. That means it uses some of the energy of the system, and, you know, you keep going down and lose those energies through the friction, and at the end, when you go to the last few meter, there's a stronger brake to stop. Now here, we have one of these hanging systems. The guy sits here. It has an initial velocity of V0 and initial height of h. All the values are given. So V0 is 4 meters per second. H is 12 meters. It's going to go through a loop with the radius of 5 meters. So as it goes down here, it gets the maximum speed because a lot of potential energy will turn to kinetic. It's going to go back up. Some of the kinetic will be turned into potential. You remember T plus V is constant. So if T increases, V has to decrease. And if, like when you go up and V increases, T has to decrease. Because it's smooth, I guess somewhere it should say, okay, neglect friction. Okay. You neglect the friction and the size of the car and passenger. This means you treat this as a particle. We want to find out their speed when they are at the top of the loop. So they come here all the way down, make half a circle, you get to this point, and at this point, you want to see how much the speed is. Okay. It also wants to find the reaction of the 70-kilogram passenger on his seat. So obviously, when you sit on a chair or a seat, your weight is tolerated by the seat, but that's static. When you move around, then you have dynamic forces, you have acceleration, that force may change. To kind of give you an idea how that dynamic force may work, you guys all have been into an elevator, right? When the elevator goes up, what do you feel? For example, you are in an engineering building, you want to go from the lower level to the first or second or third. Especially our elevator is kind of slow because we have only 2-3 floors, right? When you go to high rises, that there's like 15, 20, 30 floors, right? It may have to go faster. It may have to have a bigger acceleration. What do you feel when it goes up? What do you feel when it goes down? Anyone can describe that? Should I call someone? Or you're gonna get, how about the majority of the class? Kelly, when you go up, what happens? What do you feel?
You feel heavy because it's like pushing on you.
It pushes you up. Technically, when you go up, you have an acceleration upward. You have your gravity force downward. So the reaction force has to compensate the gravity and be extra to push you with acceleration going up, right? So that's what you feel heavy. Sometimes I feel like I'm bending my knees because if it's still strong and I'm damn old, right? So that's what I feel. And when it goes down, the gravity helps to the acceleration going down. So the reaction force is going to be less than your weight. So you feel lighter. And you don't feel it all the way through because at the beginning you have some acceleration, specifically for high rises. You get to some speed and then the speed is constant, you feel normal. That is what happens when you have acceleration and the reaction of your interaction with the floor, if you sit on something, will change. The problem wants to find that reaction force when you get right at the top of here. So is that the definition of problem clear? Okay, so let's go to the tablet. I think you may have written the notes and kind of gotten the information here. So what we have here is this. You will start from this point. Let me just kind of roughly draw this roller coaster. This is point A. So you are here like this small square. And then this is H. This is rho. H is 12 meter. Rho is 5 meter. The mass of that guy is 70 kilogram. And you want to see how much his speed is when he gets to point B. You remember when we start talking about work and energy relation, I said, unlike Newton's second law that you solve it at one particular moment, like what you did in your quiz, you solve the problem at one moment. Here, there's no one moment. We're going through a path that goes from A all the way to B. Now, you may realize if you want to use Newton's second law, good luck with that, because this is a very weird curvature. You have to have your acceleration in terms of the radius of curvature and everything, and it's very complicated to do it. But if you do use work energy relation, so let's say using work energy relation, first of all, do we have any non-conservative force here? Is there any non-conservative force?
I think gravity.
Gravity is non-conservative?
Oh, yes. Sorry, Lisa.
That's okay. That's okay.
Sorry.
So we have only gravity here, right? You have reaction forces as this goes around, right? You have reaction forces everywhere. And we want to find that, are reaction forces conservative or non-conservative? Someone say something. Like Ricardo, the reaction forces are conservative or non-conservative?
I think those are non-conservative.
Well, it's a tricky question. Fundamentally, because it's not gravity and is not spring force, and maybe some electromagnetic forces may categorize as, you know, conservative. So you may say if it's not those, it's non-conservative. But the trick is here. What is the work of reaction force? Because we want to calculate the work, right? What is, or how much is the work of reaction force? Go back to your notes. Do you guys print the slides? If you print the slides, go to slide number 8. And it talks about the forces that do not work. One of them is the reaction force, because reaction force is usually perpendicular to the path of motion and does not work. So you may say reaction force is not conservative, but it doesn't even do work. So probably is like a third category of none. If there's no friction, if there's no pushing or pulling, the only thing we have is gravity. So all the forces are conservative. So if you write P1 plus V1 plus summation of U1 to non-conservative equals T2 plus V2, practically this is 0 and you get T1 plus V1 equals T2 plus V2. And 1 is point A, 2 is point B, like that. Let's just find those terms one by one. How much is T1? It's going to be half M V1 square, and this is V1, VA. Let's just make it VA square. You have the number. I'm not going to calculate the number right now. Okay. How about V1? V is the potential energy, right? It should have gravity in it, and it should have spring. We don't have a spring here. It's going to be just gravity. So we're going to get mgya. Now here's the question. Where should I put my reference to measure y? Because remember, y is the y component of the coordinates in XYZ. Where should I put my coordinate system? Should it be on the ground? Should it be in the middle of, let me ask you a question this way. Is the coordinate system like y, I should measure it from here? Maybe I should measure it from here. Maybe I should measure it from here or somewhere else. Which one? Let's say situation 1, 2, 3, and 4 is none of the above. Which one you choose from 1 to 4? And I'm going to ask Haoshen.
1.
1.
Yeah.
Do you agree with 1? Can I use 2?
Yeah.
How about 4
Uh,
or 3? Remember, usually when you have V1 here as mgy1 or h1, you're going to have mgy2. So at the end, y1 minus y2 is that something that matters, right? So because of that, it really does not matter where you put your reference point or reference line for y. You have to just pick something, right? Now, here, I could pick any of those, but it might be easier from, calculation perspective to pick this guy as my reference for y. If that's the case, then here you're going to get mgh. And h is given. I could go here, and then y1 would have been h minus rho if you go from the blue reference, right? This height is h minus rho. Still, you can do it, but that minimizes the green one minimizes the calculation. Now we're going to go to T2. I do not know the velocity at point B. Technically, that is what I'm looking for. So it's going to be half mvb squared, and V2 is going to be mgyb, which is mg2 rho. Okay. Any question about these 4 terms? So I find T1, V1, T2, and V2. Now I'm going to substitute it into the main equation. As I said before, I don't know if you remember, last time I said work energy usually gives you one single equation, which is this guy. So you're going to get half mva squared plus mgh equals half mvb squared plus mg2 rho. And the unknown here is going to be VB. I'm going to give you like 1 minute to calculate this. And please, everyone, try to do this, because when you put the numbers here, you become more familiar with the equation and how to use it. And if you solve it, you should get this number. Please let me know if you get the same number or I may have done it wrong.
I got the same number.
Yeah, looks good. The second part of the problem, any question about this? So technically, if you practice 2-3 problems like this, and the entire time I spent to explain, you know, the reaction and everything, if you don't need that, you can solve this in 2 minutes. Start with this equation, get these values. You even don't have to write them separately. I always write them separately for students to see. You can simply substitute the numbers here and solve it. Okay. The second part of the problem asks the reaction force when the guy is at point B. And because this, if you remember, this was kind of like, you know, this type of hanging things that they sit here. I probably my drawing skills should be a little better. But so if this is like the chair or the seat coming here, then the guy sits like that, right? Now, if you go to B, I'm going to redraw B here. In B, the guy will be upside down. Okay. So if that's the case, the seat is going to be like that. And the guy will be upside down. Like sitting like this. Can you visualize this, right? So I'm going to redraw that thing here. So this is the seat, kind of hanging somewhere. And this is the guy sitting here. Very happy, enjoying the ride. Okay. And his hands in the air, like, woohoo. And possibly screaming from the bottom of his lung. So this is the case, right? The problem asks to find the reaction force of the seat. How do you find this? Any suggestion? Come on, guys, say something. We are in chapter 14, which talks about work energy. But anytime you talk about force at certain point, possibly what we should think of? Newton's second law, right? So if this guy is here and look at this path of motion, this is the path of motion for that guy right here. It's a circular path. So the first thing is I'm going to get the free body diagram of this guy. So because I'm lazy, I'm just going to delete or remove the seat. Okay. And for free body diagram, you have the gravity force, which goes like here. And you have the reaction force from seat on the guy, FR, reaction force, right? and it moves on a circular path. So technically, if this is path of motion, and let me just use the grid. If this is the path of motion, you're going to have ut, and you're going to have un, two perpendicular directions, right? T part, I don't care as much because I'm looking for this reaction force, which is a normal direction. Therefore, if I write summation of forces in N equals M AN, in N, you're going to have FR plus MG, right, is equal to MV square over rho. And the V we have is here. So technically, FR is MV square over rho minus mg. And if you substitute the values of 70 kilogram, 7.432 square divided by 5 minus 70 times 9.81, you're going to get your FR as 86.7 Newton. Any question? Now, I want you guys to pay attention to this part. Reaction force is mv squared minus mg. What happens if this term is smaller than this term? For example, instead of 7 point something meter per second, you go to, I don't know, 2 point something meter per second. And this becomes much smaller. It becomes less than the gravitational force. What happens? FR becomes negative, obviously, right? Can we have a negative FR here? Come on, guys, say something. It's not rocket science. It's as close as you can get because rocket science is also dynamics, but can FR be negative? Remember, I don't know if you can see my hand. Let's say this is the seat, as this is the person sits here. When you sit here, you create compressive force, right? So the seat pushes you up. Negative force means the seat pulled you down. You cannot do it unless you're glued to the surface, right? So practically, if mv square over rho is equal or maybe smaller than mg, then the passenger will fall and can sue Disney for millions if survives, right? Which means the smallest speed is when mv square over rho is equal to mg, which means v is equal to the square root of rho g. If your velocity goes below this, you're going to fall. So the idea is anytime you have a full loop that goes like that, you have a speed of v bigger than this guy, right? You may have seen some of this attempt. They have small loops in the street and they try to go with roller coaster or something. Sometimes they go here or they go here and fall. Why? Because that speed is not good enough to take them all the way through. So technically, the potential energy, the kinetic energy they have, they get here or here, makes zero speed. All of it goes to potential and the guy falls. Even if it's not zero, you need to have certain amount of speed to be able to complete the loop. That's how they calculate the size of these loops. And some of this stunt, they do it with bikes or with motorbikes, or I've seen a couple of times they do it with even cars. For the car to be able to go all the way here, right? And it's not the best car, obviously. It has to have a speed bigger than this so it doesn't fall. So you may want to go slightly above that for safety factor stuff to make sure there's enough, compressive or force between the base and the vehicle or the passenger, whatever you name it. Do it. Does that make sense? Any question about this problem? Okay, let's go back to slides, do another one. I'm going to do this one. You have a horizontal force that is also constant. The magnitude is given 150 pounds, is applied to this system. Well, this has a 30-pound weight, this ball, and rests here when theta is 60. When we push this, this is going to rotate going up, and theta becomes smaller. We want to find the velocity of ball when theta is 0, which means this goes upward completely vertical. The sizes and everything is given. I'm going to give you a minute to draw this. How do we solve this one? Any suggestion? So to solve this problem, of course, this is again in chapter 14. So you're going to go with work energy stuff. But the question is how we're going to do this. The first question might be, do we have any non-conservative forces? Or maybe we don't. Colin, do we have any non-conservative force here?
No.
No. What was the definition of non-conservative force? Their work depends on the displacement, right? Not just the path, sorry, depends on the path, not just the displacement. So, and we said specifically gravity and spring force are conservative. Other forces, I think I mentioned a couple of times, like pulling and pushing and all those external forces are non-conservative. Do we have any pulling and pushing force here, Colin?
Yes, P.
Yes, force P. So technically, force P is non-conservative, right? Now, let's switch to the slides, to the tablet. This is how the problem looks like, right? Now, as you push, so the first observation was force P is non-conservative. Right? The mechanism that moves this is a parallelogram. So this and this are the same. This is 18 inch. So you have the dimensions. And I mean, I didn't draw this scale. So theta 1 is 60 and theta 2 is 0. To get to the 0 theta, and I try to draw this with red. So practically, this mechanism is going to look like this. Kind of like everything goes in a line. These guys come here, this guy come here, and this guy goes there, right? Can you guys visualize this? It's like 60 degree, you turn it all the way up, it becomes perpendicular like this, and that's how you go. So now the next step is to write down the equation. Because we have non-conservative forces, I'm going to have to write T1 plus V1 equal, sorry, not equal, plus summation of U12 non-conservative equals T2 plus V2. The problem says that the ball is initially at rest. I was looking for that thing to find T1. So if that's the case, T1 is going to be 0. T2 is going to be half mv2 squared. V1 is going to be mgy1, and V2 is going to be mgy2, right? And summation of U12, because the force P is constant, Okay, because the force P is constant, it's going to be force P times goes from here to here. This is going to be its delta X. Let's call it delta X. Any question about this? And remember, I do not consider the mass of these rods. We suppose they have no mass. The only thing that has mass is the ball, right? Goes from here to here. So we neglect the mass of the green rods or bars. Any question about these 4 terms? Or 5 terms? Let's find them one by one. The first question is, I use the expression y1 and y2. Where should I put my reference point? Where do you guys put the reference point? Should I put it here? Should I put it here? Maybe I put it here, here, right? Again, you have multiple options. To make it easier and to be able to calculate this, I'm going to use this as my y reference line. If that's the case, this will be y1 and this will be y2. Okay, can you see that? This is y1 and this is y2. Okay. Now, and also in the problem, it gives the weight as 150 pounds. We need to find the mass. Then we 150 divided by 32.2. And if you calculate that, 150 divided by 32.2 is going to be 4.658 slug.
Is the mass supposed to be 30?
Let me see. I think I may have written the wrong number. Let me double check. Yes, mass is 30. The force is 150 pounds. Thank you. So this is 30 pounds. So it's going to be 30. And it's going to be 0.932 slugs. Thank you. So if I calculate y1, remember, if this angle is theta, this angle is also theta, which is 60. How much is this angle? Alpha is going to be 30 at the beginning, right? So y1 is going to be 18 times sine 30, which is going to be 9 inches. Y2 is going to be the whole length here. It's going to be 18 inches. So I'm going to substitute the values here. T1 is still 0. T2 half 0.932. V2 square. V1 is mg, which is 30 times 9. Now, this is 9 inches. Should I keep inches or should I turn it to foot? Remember, the unit for work energy was pound-feet, right? This is inch, so you're going to have to make it feet. And V2 is going to be 30 times 18. And delta PX, if you look at this, this is your delta X. This is the angle theta. So delta X is going to be 9 inches times sine 60, which is going to be 7.794 inch, and your U12 is going to be 150 times 7.794. Again, this is an inch. We divide it by 12. And if we do that, and please do the calculations because again, as I said, I use my phone, not the best thing. So we get all the values here. I'm going to highlight them. T1 is 0, T2 is this much, V1, V2, and the work of non-conservative forces. So if you substitute all of that in the equation, you're going to get 0 plus 22.5. This is T1. This is V1 plus 97.43. This is U12 equals T2, which is half times 9.3. Let me just calculate that. 9.932 times half. Point 466 V2 squared plus this is like T2. And V2 is going to be 45. Okay. And from here, you can get your V2. And let me know how much it is. Let me see if you get the same number.
Yeah, I got the same number.
Any question about this? So this was an example that had the work of non-conservative forces. As you could see here, it had potential energy and kinetic energy. There was no spring, but if you have a spring, you can calculate its work, no big deal. Can you do something like this in the quiz? Because we may have another quiz next Wednesday. Or maybe we can do it even, today's Wednesday, right? We can have the quiz on Monday. Any question? Okay. Are you guys done writing this? I take it as yes. Let's do this example. This has also a spring in it, so you may want to have some spring stuff practice. So in this problem, as you see, you have a pan here. It has negligible mass, so when we go from for gravitational potential energy, it doesn't have mass. You have two springs. The stiffness is given. You have a 10-kilogram box that is half a meter above the pan. You release this from here. It comes down, hits the pan, and because of the springs, they go down and stretch up to here. The problem says find the maximum vertical displacement D. And it says initially each spring has a 50 Newton tension. So these springs are not in neutral sheet. This 1 meter is not their neutral length. They have some stretches in them. Okay. How we solve this one? When it comes to work energy, as you have seen, usually the question is, do we have non-conservative forces? Do we have non-conservative force here? Let me go to the, did you guys write the whole thing? Took the notes? Okay. Let's go to the slides. Or to the tablet, actually. So this is how the problem looks like, okay? The position 1 is here, and position 2 is here. In position 1, this guy is up in the air. The springs are horizontal. In position 2, the guy is here. The springs are stretched. Okay. If you look at here, we have only gravity and spring forces, no friction, no external forces, no pushing and pulling. So there's no non-conservative force, which means you can use the conservation of energy, work energy, T1 plus V1 equals T2 plus V2. T1, if you release the box, the moment you release it, it has no velocity. So T1 will be 0. How about T2? The problem says to find the maximum value of D. So I don't know if you can see my hands. If this is the spring, the box hits the spring, they go all the way down until it temporarily stops and maybe it bounces back. That is the maximum displacement. So if that's the case, at point 2 also, the box has 0 velocity. Okay. Usually, this is how you determine if the velocity is 0. Goes to the maximum things, maybe stopping there and kind of bounces back. But at the bottom, the lowest bottom point, the velocity is 0. How about V1? We have a spring and we have gravitational potential energy. For the spring, again, these are my 2 springs, right? The purple thing. How much is their initial deformation? The problem does not give the deformation, but says initial spring force is 50 Newton. Can I use this to find S1, the initial deformation of the spring? Of course, you have the force, so S is going to be F divided by K, which is 50 divided by 250, and your S1 is going to be 0.2 meter. So V1 is going to be half. Let me write this down here. V1 is going to be, because we have 2 springs, we're going to get 2 half K S1 square, right? I'm not going to put the numbers right for now. We calculate them, but we can substitute later. We also have gravitational potential energy. This guy is up in the air, right? How do I find the gravitational potential energy? To do that, I need to have my reference point, right? Which point is better to choose as reference point? You may say, I'm going to go with here or here, but to make it kind of nice, I'm going to use this level as reference for Y. So if that's the case, then your gravitational potential energy is going to be plus mg this height, h, which is 0.5 meter. Okay. This was the h I used here, half a meter. Now we go to V2. Springs are even stretched more, both of them here, as you can see. So we're going to get 2 times half K S2 square. How about Y2? The Y position for this guy, this is like Y2. How much is Y2? Hi Z, how much is Y2?
Let's see, Y2 is D.
Is equal to D. We need to determine that. Yes. So you're going to get, is it plus or minus? Cristobal, is it positive or negative? Y2 is positive or negative? Or anyone else?
It's negative.
Why? Because we are below the reference, so it's going to be negative. Thank you. So now I put S2 here. I need to find S2. Now, to find S2, I'm going to look at this geometry. Please pay attention to the tablet. I'm going to separate this part and redraw it down here. So this is the spring in position 1, right? Which is 1 meter. This is the position 2. This is D, and this is L2. How much is the neutral length of the spring? Is it 1 meter? The unstretched compressed length of the spring, how much is that one? Because to find S2, technically S2 is going to be L2 minus L0. We need to find L0. Jake, how much is L0? I probably should call you guys Jake B and Jake Z just to make it short. Now I'm going to ask Jake Z. How much is L0? Okay, your mic doesn't work, but you may want to type it here. You know what? I'm just going to go to Jake B. The other Jake, how much is L0? Oh, I can't hear you either. Okay. Remember, this was the length in horizontal position. We found the deformation in horizontal position 0.2. So technically, your L0 is 1 minus 0.2, which is 0.8. So your S2, right? Your S2 is going to be L2 minus 0.8. But how much is L2? If you look at this triangle, right? Your L2 is going to be a square root of D square plus 1 square. And if I substitute it there, your S2 will be square root of D square plus 1 minus 0.8. I'm going to substitute this value here and rewrite V2. Okay. So I got T1, T2, V1, and V2. And I'm going to substitute those values into this equation. And if you do that, I'm going to write it with blue. You're going to simply get these two cancel out each other. K S1 square plus MGH equals these two cancel out each other to K just like that. right? You may realize that this is a nonlinear equation, which is okay. You can expand this, right? You get k times d squared plus 1 plus 0.64 plus 1 minus 1.6 the square root of d squared plus 1. This is the whole thing, minus mgd, and the other side is k s1 squared plus mgh. Now, if you look at this equation, s1 we calculated already, 0.2, h is given, the k value is given, the only unknown is d, which appears here, here, and here. Okay? So if you simplify this, if you put all the numbers and simplify it, you're going to get this equation. You are going to get 250 d squared minus 98.1 d minus 400 square root of d squared plus 1 plus 350.95 equal to 0. This does not have like a straightforward solution. You may want to have to take this to the other side, make this square. It gives you a problem of order 4. Obviously, you're not going to get something like this with this level of complication in the test, but I thought this is a good example to show you how you do it. You can solve this with any nonlinear method. If anyone here knows how to use MATLAB, the programming, software, MATLAB. No one uses MATLAB here. I think you're going to get a course for like numerical programming, and you will learn how to do MATLAB. You can solve it there. You can solve it with any technique. I'm just going to give you the number. The D that satisfies this equation is 1.34 meter. Any question? Can you solve something like this in the exam? Of course, except this nonlinear part. Remember, we started with initial and final position. We determined there's no non-conservative force. So this is my equation. I got my T1, T2, V1, V2. The rest was calculation of, the parameters from geometry, from other information, getting all the way into this big equation and solve it. Any question about this? Okay, let's go back to the slides. Let's do this example. This is kind of short, and hopefully reminds you some other stuff. You have a mass with an initial velocity of 8 feet per second. You have two springs with stiffness of K1 and K2. Right? And this mass comes and hits them. Each of them has its own stiffness coefficient. We want to find the maximum deflection of plate A. So this is A, this is B. We want to see if this guy comes and hits this, it's going to go, becomes like this. Right? All the way here, where this is like plate A and plate B. So we want to see how much this delta S will be. The initial velocity is given as 8 feet per second. And it has the weight of 100 pounds. So let's go to the slides. So obviously, this is position 1, and this is position 2, right? In position 1, your mass has the velocity, but the springs are uncompressed. In position 2, but again, it says maximum deformation. So we are expecting that V2 is going to be 0. And because there's no non-conservative force, I'm just going to write the equation T1 plus V1 equals T2 plus V2. T1 is half mv1 squared V1. The initial potential energy is 0 because the springs are not compressed. T2 will be 0. And V2, you have two springs, half K1 S1 squared plus half K2 S2 squared. Right? These are the four values. Any question about this? Can you do this now? Just getting T1, V1, T2, V2, like that. I'm going to plug all of this into this equation. So you can get half mv1 squared is equal to half K1 S1 squared plus half K2 S2 squared. So you get one equation. And as you may realize, we have two unknowns of S2, S1 and S2, right? Two unknowns, one equation. How we're going to get the second equation? You guys remember anything about parallel series springs? Maybe not. Here's the thing. Look at plate B. If I get the plate B here and get the free body, remember B doesn't have any mass, but even if it does, at the end, the velocity is 0, it kind of stops there, still doesn't have mass, so you don't have any acceleration. From the right side, you have the force of K2, S2. From the left side, you have the force of K1, S1. And because plate B has negligible mass, technically summation of forces in X equals MB AX. This is 0, which means K1 S1 equals K2 S2. So this gives you the second equation. For example, from here you can calculate S2 is K1 over K2 S1. Substitute it here to get half mv1 squared equals half K1 S1 squared plus half K2 K1 over K2 S1 squared. You can get rid of all the halves, this and this and that. So you're going to get mv1 equals K1 plus K2 K1 K2 squared all the way times S1 squared. And you get your S1 and S2 calculated. You guys give me the numbers. And I know we're a couple of minutes above the time, over the time, but you owe me a few minutes from last time, so I think we can spend another 5 minutes to finish this. If you calculate this, your S1 is going to be 0.772 feet. Your S2 is going to be 0.515 feet. And the overall displacement of this guy, look at here for a second, please. The overall displacement of plate A that we have, this delta S, oops, is the summation of S1 and S2. So your delta S is going to be S1 plus S2 and will be 1.29 7 or 29628 something. 1.2 87 is going to be 1.287 feet. Now, do you guys remember how to get the equivalent spring if you have two springs in series or parallel? For example, if you have something like this, K1, K2, and you apply force and displacement, your equivalent K is going to come from here. 1 over overall K, if you want to simulate this or replace this with just one spring, so 1 over K is going to be 1 K1 plus 1 K2. And if you have two springs in series, sorry, in parallel, K1, K2, and you apply force and get the displacement, the equivalent of this is simply K is K1 plus K2. Okay, so you could use this guy for this problem, but if you don't remember it, we just got it through the forces. Any question? So we are done with this chapter. And on Friday, we're going to start chapter 15. Okay. I will grade your homework and quiz this weekend. I will post a set of homework, maybe fewer as we talked about it. And it will be due on Monday, so you have like almost 4 or 5 days to finish it. Meanwhile, if you have any question about the concepts, please feel free to let me know. We can find the time to meet through this Zoom and address your questions. Looks good? Did you guys enjoy the lecture? I see few of you feel sleepy, like yawning all the way, right, Kelly? It's okay. Okay, so I see you on Friday, and we start new chapter, and enjoy the rest of your day. Goodbye.